We will now be working through the Independence of Dimensions lab. You can find this on the next page of your note packet. This lab does not need to be done in your lab book. Instead, I have provided space on your note page for you to show all of your data collection and data analysis. So again, you do not need to write anything in your lab book. This lab is going to be done entirely in the note packet. Usually, I would get the school computer cart and have each of your groups work through this lab on your own. But because I'm going to be out of town, I thought it would be simpler if I just help you with the data collection, and then in your groups you can work through the analysis yourselves. The objective of this lab is to use technology to analyze the motion of an object that is moving in 2 dimensions. We started today's lecture by looking at a basketball, so it makes sense that this lab is also going to analyze a basketball. Step 1 is to videotape a projectile object that is moving in both the X and Y dimensions. This has already been done for you. If I click on Watch Movie, we can see this basketball in slow motion moving towards the hoop. Notice that the player makes his shot. I actually had to film this several times because he kept missing, but eventually he did it. Step 2, we are going to use a computer to create an accurate motion map for the object. In real life, basketballs move so fast that it's hard to know exactly what path they followed. However, technology gives us the advantage of slow motion. We can look at this basketball 1 frame at a time. All that I need to do on the computer is click on the basketball. So I'm going to take the mouse and go to the center of the basketball, and I'm going to click. Notice this leaves a bright green dot. My data table just recorded some information. At time 0, the X position was 0 meters and the Y position was 1.97 meters. The reason we have an initial Y position is because of the height of the basketball player. That's the distance from the green dot to the gym floor. Now that the screen has progressed by 1 frame, the basketball has moved. Notice it's a little bit blurry because I didn't have a good high-speed camera, but I can still find the center of that blur and click. Notice it left a second data point. After 0.07 seconds, the X position and Y position have changed. We record the X position and the Y position separately because of the independence principle. We know that the horizontal motion and the vertical motion are completely separate, and so we have to deal with them individually. I am going to continue following the center of this basketball as it moves forward, and the computer is continuing to record my data points each time I click. Isn't technology wonderful? And we've reached the hoop. Those of you that think this looks like a lot of fun and you're really disappointed that you don't get to do it yourself, don't worry. You can always go home and do this lab on your own time. The URL for this lab is in your notes next to the instructions for the Independence Lab. So if any of you are interested, you can do this at home. Notice that if I watch the movie now, it will actually show me the motion map as it forms, or I can click through one frame at a time and follow the path of the ball. It makes a beautiful parabola, just like we talked about earlier, as the ball moves forward with a constant speed, but gravity causes acceleration in the vertical direction. In your lab write-up, there's a box that says Draw Motion Map here. If you haven't already done so, please take a moment and sketch this picture. It doesn't have to be perfectly accurate. I would make a stick figure of the basketball player and then a series of dots that form a basic rainbow as it moves towards the basket. Make sure you number the first dot 0 so that someone that looks at your motion map will know which direction the dots were going. You do not have to copy the data table. That would take forever to write those numbers down. So we're just going to leave them in the computer, and that is good enough for us. We have barely started this lab. The real science that we need to do is the data analysis as we start to interpret what all of these numbers mean. Now the computer is going to help us out. If I scroll down the page, I can ask the computer to draw some graphs for me. It's using the data from my data table, and instead of making me plot these graphs by hand, the computer is going to plot them for me. So I am going to select position in the X dimension, and here is the graph that forms. In your notes where it says data collection, there is a place for you to sketch the position graph in the X dimension. You do not have to copy down the exact graph, meaning you don't have to write down the numbers on the scale, but I do expect you to plot the basic shape. Notice that the dots are forming an upward diagonal, and it looks like it has a fairly consistent slope. In other words, it's straight. It does not appear to be curving. So again, in your notes, make sure you sketch this graph in the appropriate table square. This graph is only showing half the story. There's also the Y dimension to look at. So I'm going to switch over to the Y dimension, and notice the graph that forms is a completely different shape. You don't have to copy down all the exact numbers, but I do want you to notice that the graph starts with an initial height of about 2 meters, and then the dots go up, forming a rainbow, and then they come back down. Notice the Y position graph looks very similar to the motion map. This will not always be true, but in this particular example, they do form a very similar shape. Because this graph is curved, I know that there must be acceleration. Remember that acceleration is what makes a position graph bend. Now we're going to look at velocity graphs. So I'm going to change to velocity in the X dimension. Remember that velocity graphs have 2 quadrants. So when you sketch this graph, make sure you form both quadrants. Once again, you do not have to record all of the data numbers on the axis, but I do expect you to sketch the basic shape. Notice all of these dots are clustered around the value of 4. Some of them are a little bit more than 4, and some are a little bit less than 4, but they all cluster near that value. The computer is actually calculating the average for us. If I look in this box, it's telling me that the average value was 4.1. Please write this number down near your graph so that you don't forget it. So the average velocity in the x dimension was 4.1 meters per second. Now that's telling us something important about the basketball, and you're going to have to identify what that is when you do data analysis. The last graph that we're going to look at is y velocity. Once again, you need to sketch this graph in your data collection. Notice it has a completely different shape than our horizontal velocity. This is because the dimensions are independent. They have no influence on each other. In this example, we start up around +5, and then the graph slopes downward, crosses into the negative quadrant until it reaches about -4. This point here, where we touch the 0 axis, is the turning point for the ball. This would have been the highest point in our trajectory. Remember that as the object moves up, it has a brief moment in time where it stops moving before it falls back down. So this is the moment where the velocity reaches 0, and then the ball enters the negative quadrant, which means it's coming back down. This graph looks like it has a pretty consistent slope. In other words, it looks fairly straight. It's not curving. And the computer is actually calculating that slope for us. So notice this particular graph has a slope of -9 meters per second squared. Now that number should look kind of familiar to you. It's not a perfect match, but it is very close to another number that we've talked a lot about this year. And you're going to have to identify what that number is when you do your analysis. Please write this number down near the graph so that you don't forget what it was. All right, data collection is done. You should have drawn graphs in each of these boxes on the left. Now we're going to do the hardest part of the lab, which is say what all of these numbers mean, or what the graphs mean. So the data analysis column, this is where you're going to get most of your points. I am going to help you with the first graph, but then you are expected to finish the rest of the graphs on your own. So our first graph, let's see here. I'm just really quickly going to sketch it. Okay. If the computer will do what I want it to do. Insert. All right, you should have already drawn this picture. I'm just copying it down again. Our first graph looked kind of like this. So our job is to say what that means. In the explanation, I'm going to say that the graph slopes uphill at a constant rate. I can see that just by looking at the graph. But what does that mean? This means the object is moving forward at a constant speed. Okay? I used the word forward because this was in the x dimension. Okay? The word forward is associated with horizontal motion. You would never use the word forward if you were looking at a y dimension graph because it's not the correct vocabulary. All right, I did that first explanation for you. What I need you to do now is, if you're the sub, please pause the video and give the students several minutes to write explanations for the rest of the graphs. What you need to tell me is what the shape of that graph is telling us about the basketball in the real world. If we wrote down a number with the graph, I want you to tell me what that number means. And then when the students are finished, you can turn the video back on and I will show you some answers and we can finish our lab report. So pause the video now. All right, you should have had some time working with your groups to write your explanations. I am quickly going to jot down some possible answers. You don't have to have the same answer as me, but it should be similar. Okay, so the graph goes up, then turns and comes back down. This means the object starts out moving upward and ends up moving downward. Notice, because I'm in the y dimension, that I'm using the words up and down. We would not use the words forward or backward. On your velocity graph, the graph has a constant positive velocity of 4.1, was it? I don't remember. What this means in real life, so this means the basketball is moving forward 4.1 meters per second. So this was the forward speed of the ball as it crossed the court. Finally, the last graph, so the graph starts with positive velocity and ends with negative velocity. The slope is -9. This means the basketball starts out with a lot of upward speed and ends up with a lot of downward speed. The acceleration from gravity was -9 meters per second. Notice that I connected the word gravity with the number that we saw. Now, we've learned in class that gravity is actually 9.8. So this match is not a perfect match. Okay, in fact, we're looking at about 92% accuracy. Even though it's not a perfect match, it still is a pretty good result. I would guess that what's happening here is air resistance is contaminating our results. Make sure that the data analysis you wrote down mentions some of these important facts so that you'll get full participation points. To finish off the lab, we just need to answer a couple very simple questions. Did gravity have any effect on the horizontal motion of the ball? In other words, did the x graph show any signs of acceleration? And the answer is no. The x graphs showed no sign of accelerating. Okay, this is because gravity is trapped in the y dimension. It cannot influence what the ball is doing horizontally. Finally, does it appear that the two dimensions have any influence on each other? In other words, did the x graphs and the y graphs look like they somehow reached across dimensions and changed what the other one looked like? And the answer is no. Each graph did its own unique thing. This is the independence principle. The horizontal and vertical motion are completely independent. They have no influence on each other. Finally, our evaluation is where we need to mention things that may have gone wrong or that may be limiting our results. I'm going to say my camera was not good for high speeds, and air resistance is contaminating our results. But we still got a 92% accuracy for gravity. Okay, I'm just acknowledging that our results weren't perfect, but they were still pretty good. As a scientist, you always need to evaluate any data that you collect and acknowledge weaknesses. This is what we do in our evaluation. This is the end of our independence lesson. If there is still time left in class, then please find something quiet to work on. And you will learn more on Wednesday.